Before we begin our discussion on pointers, we must at first try and understand how variables actually work themselves. When we declare a variable, we tell the compiler the type of the variable, let's say it's int in this case, and the name and symbol of the variable. In this case, it's n. When we do this, we ask the computer to set aside the memory required for the type int. On 32-bit computers, a single int demands 4 bytes of memory. You can check how much memory int demands on your computer like this. In my case, as you can clearly see, the size of the int in my computer is 4 bytes. I have provided this entire presentation and the transcript to this video in the description below. This video is a part of a course that I'm making for people who want to understand the basics of using pointers in the C programming language. If you want to be notified about the course and get the presentations and transcripts to all the course material, join my email list by filling the form in the description. Alright, back to the video. Let's get back to our int n. The compiler checks the type of the variable and sets aside 4 bytes of memory to hold the value of an integer. A symbol table is also created, and in this symbol table, the name of the object and the address reserved for the value of that object is also stored. So eventually, when we give n a value, for example, right here, we check the symbol table, we find out where the memory reserved for an integer, which we call n, is reserved in memory. We go there and store the integer 2 in the 4 bytes that we've reserved to store the integer 2. An object is a named region of storage. You can think of the object n in 2 ways. First, it holds the specific number, like 2 in our example. Second, it has a location in the computer's memory, sort of like a home address. People often use terms like R value for the number it holds and L value for its memory address. These terms help us talk about these two aspects in programming and computer stuff. More accurately, the L value refers to the variable n and the address it refers to in the symbol table where the object's assigned value is stored. So if n is used on the left side of the assignment operator, or as I like to call it, the as operator, its L value will be used. The R value is the value to be stored in the memory address or at the memory address reserved for the data type itself. For example, after the assignment n equals to 2 in the program, the R value for this object is 2. Let's understand this using an example. In this example, in line A, we can start reading this line from right to left. So as you might already do yourself or try yourself, 24 is assigned to the address of A. This is how we read it. That's why we only talk about the L value of A, because it's on the left hand side of the assignment operator. Therefore, its L value will be used. And L value is the address where the memory has been reserved for this variable A. Got it? In line A, the compiler understands the A object as the address of the memory reserved for the int type in the computer. Let's say that A's address is 200 and B's address is 204. So in line A, the compiler literally interprets and generates the code as such. Put the value 24, which is on the right hand side of the as operator, to the address of the memory reserved for the A object. Here, since we want to use the address of the A variable, we use it on the left hand side. Before we talk about our intention with line B, we should talk about what the compiler will interpret here too. The compiler will see B on the left-hand side of the assignment operator, the as operator, and will know to use the L value of B, which is the address where the symbol B points to in memory, which we assumed earlier was 204. It will notice A on the right-hand side of the as operator and will know to use the R value of the named symbol A, which in this case is 24. In short, this code will generate even lower level code to put 24 at the address of the object A, and then take the R value of A and place it at the address reserved for an integer named B. We have spent a lot of time not talking about pointers when the whole point of this video is pointers. So let's begin. Let's take this example. In this example, what I want to do is to store the address of the variable A, as in the address that A points to in the symbol table, as the value at the address of B. I know, that's very confusing. What I want to do is, instead of assigning 24 to B, I want to assign the address of A to B. But the thing is, C just won't let us do that normally. Let's start from the beginning. We have been storing constants like 2 and 24 as the R value of the objects. The R value for A is where the address of A points to. But hear me out. What if I want to store the L value of A, as in the address of A, at the L value of B? After this assignment, I expect the L value of B to be 204 and the R value of B to be 200 and not 24. In the line B, in the last example, we are storing the R value of A, that is 24, at the L value of B, which is 204. To do this, we cannot use simple declarations such as int n or int s. We cannot use normal variables to store memory addresses. We have to declare pointer variables for these kinds of operations. We declare pointer variables as such. PTR is the name of our variable, just like A and B were in the last example. The asterisk symbolizes our request to the compiler for a pointer variable, essentially allocating memory to hold an address. When we specify int, we are indicating our intention to use this pointer to store the address of an integer. Such a pointer is referred to as pointing to an integer. It's important to note that when we declare int n without assigning a value, n does not have an initial value. PTR is without a value in the given declaration right now on your screen, meaning we haven't stored an address in it. In this scenario, if the declaration is outside of any function, it's initialized to a specific value that guarantees it won't point to any C object or function. Such a pointer initialized in this manner is referred to as a null pointer. Now that we have reserved memory for a pointer variable or an address, we only have to assign an address to it. That's it. But how? We know that B equals to A assigns the R value of A, which in this case was 24, not the L value of A or the address of A, which is 200. We want the latter to happen. We want to assign the address of A to the R value of B, the value where the address of B points to. The AND operator tells the compiler that, hey, I know that usually using the A variable on the RHS of an AS operator leads to using its R value, which is the constant that it is storing in the memory. But in this case, although I'm using it on the RHS, I still want to use the L value of the object, which is the memory address reserved for an integer, which is in this case assumed to be 200. And now we come to the end of our discussion of pointers. Here are a few more examples. In this case, we declare an A variable and a pointer variable called B. In the A variable, we store 24, and in the B variable, which is a pointer variable, we store the address of A. Let me remind you that the L value of A is a random address in memory, and the R value of A is 24. When we declare B on the 8th line, the L value of B is a random address in the memory, and the R value of B is the address of A or the L value of A. Now, if we print the variable A, since we are printing it directly, it will use the R value of A and not the address of A. If we want to use the address of A, on line 11, you can see that we just have to add an ampersand before the A. You can see the results. Alright, thanks for watching this video. I'm glad you watched it. Here's another example. Take a look at it. Try to understand it yourself. It will help you more than if I explain it to you. Trust me. Goodbye.